Then if you are taking the processor design course, that one is done in groups, 3 students per group. Then it's a good idea to try to cluster, you know, before we start the course. I'll probably place an announcement on Blackboard on that. Okay, now let us return to the error story. Now, okay. You keep it like that? This is good. It's brilliant. Then, if I don't have enough room to represent something like, you know, this one, which is out of the short format, I may go for the long format. But this will make things even slower, and then I'll consume more energy. Then if I use that every now and then, you know, if I have errors every now and then, and I can keep them under control and I can track them, I can still live with a short format. Now, this is a very good example which will tell you how much actually away from the result you are when you do floating point calculation in a computer. You subtract 1 over 100 from 1 over 99, which when we do things, you know, should be trivial, but in computers, there are a couple of things. First of all, you know, when I'm doing the precise result, I get that, and this is due to the fact that my system is limited to 4 digits. Now let us look on the representation in a floating point number system. Then, when I'm representing 1 over 99, this is my representation. I have 4 digits in my system, and there is no more than I can do. Then I have a sin from the beginning. I didn't start with the calculation and I have a problem. For the other one, that's fine. Here I don't have an error. Now I'm doing the calculations in floating point, which means, you know, this is the representation, this is the representation. Now they will cancel, I will have something here, I will normalize, and this is my result. And you see, I have a 1% error after a very simple subtraction. And that was one calculation. And as you can imagine, this error will only amplify. I started with a 0.01% error in one of my operands, and I got 100 times more after one calculation. If I continue in this way, I better, you know, make a guess instead of doing calculation. I might be closer to the result. Now, in general, in a system where we analyze a system, a floating point system, we have something like that. We have a radix. We have a precision, which relates to the number of digits that I have in my system, and we have the approximation scheme, which, as discussed before, we usually do not select and is coming the default, but we can select. Now, there is always a kind of representation error when we represent a number, and forget about all those things here. What we would like to look at is how this error is propagated. Then, assuming that I'm computing the product of 2 floating point operands, I have an error which is coming due to the conversion of x in floating point. I have an error which is coming due to the conversion of y in floating point, and I have an error which is coming from the operation by itself. Now, if you do some kind of arithmetic here, what you see is that the errors are additive. Then when I'm doing a multiplication, actually the result will be close to the infinite precision result with some kind of additive accumulation of my initial errors. When I do a division, things are kind of the same. Okay, I have the subtraction here, but addition, subtraction is the same story. Then somehow, after this type of operation, I have an indication on how far I am from the right result. Now, if I apply the same technique for addition and for subtraction, I obtain now things which are a bit more complicated, and what I see is something which is counterintuitive. What I see is that when I'm doing a subtraction, actually my error may become unbounded, because this factor can get very large. Then in certain conditions for the operands, this can actually blow into my face. And this is called cancellation, and this is one issue which we would like not to see in floating point, but we cannot avoid it because things are the way they are. We can try to avoid that kind of situation by the way we do the processing, like the order of the processing, or by using algorithms which are kind of not effective from the point of view of the calculation, but they keep the errors under control. Then, just to make a conclusion, if I look at errors, in general, the errors are additive. And I can keep them under control, except when I see a subtraction. Because in a subtraction, in certain conditions, things can explode. And now you see here an example. Then I have a radix 10, I have 6 bits, 6 digits, and I have no guard. Now, I start with my, my operands. I do the representation in floating point, and you see already that when I'm representing y, I lost some precision. There is no room, like stuff. Now, this is my result, and this is the result when I apply addition, but this is not floating point addition. This is addition which I do with pen and paper. And now I will apply this floating point addition on those numbers, and this is my result. I shift because I have 4 lines, then I do addition, and that's it. And what you see is that this is what should be the result with infinite precision. This is what I can get, assuming the fact that I have some kind of sin at the beginning. I cannot really represent y in a proper way, and this is what I get after the calculation. Then in one subtraction, right, it's an addition, but one is negative. In one subtraction, I have a a huge error. And this is because I was actually making the error versus the ideal case. Now, if I do the error relative to what I could get from my floating point representation, it's still 900%. Then that kind of things we cannot do. Then we have to do something. And what we do is we use guard digits. Then I have now the same system. And you see the representation of the numbers is the same. But when I'm doing the calculation, I have a guard digit. And when I do now the calculation with the guard digit, my result is somehow better. Then I am still far away from the precise result, but if I now relate myself to the case when I'm processing x and y in floating point representation, which is actually what I can do, I have no error. Then only one guard digit saved me. I mean, I didn't get what I could have get if I would have had enough precision. But you know, always you need more precision and more precision. Then you have to decide at a certain point where to cut. Now there is a beautiful theorem here, and this is saying that essentially one guard bit, it's sufficient. But it's sufficient for what? It's sufficient to get the result as it would have been done with infinite precision and then rounded. That's good. No, let it play. Now, and from here, it starts the problem. We all know that, right? And when you write a program, you assume that this holds true. The associativity law, right? I assume, I mean, we learned that in primary school and we like to rely on it. Now, as you see in this example, for these three numbers, which do have a certain structure, you see, two of them are a lot larger in magnitude than another one. There are 4 orders of magnitude difference, okay, and one of them is negative. Depending on the order in which I'm doing the calculation, there is a big difference between the two results. Then what used to be, you know, an algebra law that we rely on will not hold in floating point calculation, which means that when I'm writing a program, if I'm aware about how my numbers will look, I may have to write it in a way which is not efficient in the number of operations, but it's keeping errors under control. Now, this is like an intuitive explanation of why things are happening. Depending on the order and of those operations, the contribution of C to the result is more or less important. If you first kill the guys which are in the same league magnitude-wise, which are A and B, you know, both of them are large from the magnitude point of view, then C will contribute as much as it can. And in this case, actually, because those guys are of a negative sign, they will bring you a result which is closer to the magnitude of C. If you associate C, which has a small magnitude, with one of the big guys, then its contribution will kind of fade away. Now, you can take that into consideration in your algorithm. Then when you process numbers and you have to do that kind of things, you may first check the... this is not singing.
Sorry.
The other one was nicer. Was that a phone or a...
Alarm.
Alarm. Now, it's 12 o'clock. Is it an alarm here in Europe? Then, if I look at the operands and I inspect them, I know which order should I follow, and I will try to keep things under control. Now, you can say, let us put some guard digits. And I can put some guard digits and I can do the calculation now with guard digits. I'm almost there, but I'm not there. And anyway, depending on the operands, it will always be a situation when things are not controllable. Then, okay, what do I have here? Okay, then in this one, that's another approach, and this is when you allow to work with unnormalized numbers. And that can help you in some cases, but this is complicating the story. We like to normalize numbers. Then in some cases we may allow for non-normalization, but in general this law doesn't hold true. And not only that, but also the others do not hold true. Then in other words, I'm doing a solution of a problem, algebraic, beautiful, and then I write a program which is implementing that, and then I have results which are not exactly okay. The reason is that because in your manipulation you relied on this equivalence, which does not hold true in implementation, or not all the time. You see, this is an example on how you actually compute the area of a triangle. Okay, this is the half perimeter of the triangle, and this is, you know, a standard calculation. Now, if your triangle is very flat, that will give you huge errors. And instead of doing that, you actually do this. And this is a lot more complex. You get them. Mathematically speaking, they are equivalent. However, by doing that kind of extra calculations in here, I'm trying to keep the errors under control, and I pay in delay and energy, but I obtain results which are closer to reality. Now, in many cases, what we want to keep errors under control. And this is an example which will, it's very suggestive. I'm just doing, you know, a filter. It's a sum of products. And in each step, I'm dropping like a unit in last position, which means that at the end of this, it's 1 kilo kind of loop, I lose 10 bits of precision. Then errors accumulate and they grow very fast, and I have to be aware of them. And this is another example. This is a summation algorithm. Then this is actually adding n numbers. Then instead of doing n additions, you see what I'm doing. I'm doing a lot of additions. And those are actually to keep things under control and to do some correction terms. Now, this is a different discipline. It relates to computer arithmetic, but it's not what we talk here about. It's just that you should be aware when you program in floating point that things should be treated in a different way. And there are books about that. I think there are also courses about that. I'm not sure if there is one in Delft, but people from mathematics, they deal with those things. Now, here it's a long theory about how you actually evaluate the errors, but we can safely skip it. You look happy, right? When I skip things, I see smiles. Then if I skip everything, you will be laughing here. Now, I will briefly say something about this, but very brief. If you want to have things under control and you want to eliminate, let's say, errors from the representation, you can keep numbers in a different way. You can keep them like continued fractions. And that will give you, you know, a better precision. Actually, this is a representation which is utilized, and it's saying the following. Now, I'm representing a number. It's kind of a floating point number, but I represent it like a fraction, p over q. I have a sign. I also have to have a bit to see if there is exact or inexact calculation, and then I have two numbers. I'm, you know, spending bits, and I represent the fraction directly. Now, when I'm doing calculation on that numbers, when I multiply fractions, it's simple. When I add them, I have to do, 3 multiplications and an addition. And there is even more than that. I have to normalize, because they may have common factors. Then I have a number, which is a over b, and I'm doing plus c over d. Then this will be a d plus cb over bd. This is what I have to do. They are represented with that kind of format. Okay? Then I take bits from here, then I do multiplications, additions, whatever, and then I have to store now the result in that format. But this calculation may give me numbers which are outside of the budget that I have, which means now I have to look if they have some kind of common factors. If they have common factors, I will do a kind of normalization and I represent it. Now, the advantage of this is that I can do exact calculations. There are no errors, but it's more complicated. And there is something else. The slash position is fixed. Then the budget for P and for Q, it's fixed. I can also play that kind of game and make the slash to move around. How do I do that? There is always a cost. I put here some bits, which will tell me where this slash is. Okay. Forget that kind of things, right? Have you ever heard about Dirichlet? I think you should have heard about Dirichlet. Mathematics, right? Long time ago. Okay, this is a good representation, but has complications. Another representation is to go for multiple precision. And this is essentially software stuff. Then you have that kind of things, and you can have multiple precision, variable precision, whatever for it. Now we are done with this. And for this part we are done. There are a lot of techniques which are trying to keep errors under control. And one of them is interval arithmetic. Then instead of working with numbers, you work with intervals. And whenever you compute the solution, you know that the solution is within a certain interval. And there are things, but no. We do not have the time to go into details, and it's also a bit away from the focus of the hardware-oriented course. Now let me see if I have something else for you. And I think I do. I know you would like me to skip it, but we'll talk a bit about that. Okay. Square root. No, it's a no. Now, there is another operation which we didn't speak about in integers, but which is important in floating point units, and this is square root. Now, this is the definition of square root. Then I have a radicand, which is now a 2k-bit number. I have the square root that I want to compute, and I have a remainder, which actually is not relevant. Why would I care about the remainder? When I compute the square root, it's just that I want to know the square root of the number. But the remainder has to fulfill some conditions in order for me to know that I'm doing the right job, that the square root is well computed. Now, it looks like division, but it's not exactly division. And there is something else. The remainder is representing on k plus 1 digits. and there is a justification for that. Now, I have this number, and there is nothing else. I just want to compute the square root of it. In division, I had Z, I had D, which was here, and then I was kind of computing, you know, the digits of the quotient. Now, the principle is the same. I am guessing digits of the square root in an iterative way, starting from the most significant position, and I keep on subtracting, and I will converge to the result. Then somehow things that I know from division will also fall through here. Now, let us take a look at this example, which may be a refresh if you did that in school, or might be a surprise for you that you can even compute square root without the pocket calculator. Did you learn that in school? I know you did, because you are coming from Romania, but except you, no? Okay, then if you are in a desert, right, and you want to find the shortest path, and you know the x and y, and you have to compute the shortest path, you have to square root of x squared plus y squared, right? It's like Pythagoras theorem. Then practically what you do is you split your z in groups of 2 digits. And now the way you process it is slightly different. Then you are, in here we have 3 groups. One group has only 1 digit. Okay? Now, first guess will be Q2, which is the most significant digit of the square root. And for that one, I will look for a number which, when is squared, will be as close as possible to 9, not larger than 9. And I'm lucky because the choice here was good, it's 3. Then my partial root will be now 3. This is my first iteration. Then I square this number, which is 9. I do the subtraction, and now I have a new number. Now, from now further, what I'm applying is slightly different. Now, what I'm doing is this. I'm looking for a digit, Q1, which fulfills that equation. I cannot get a negative result. Then I have to get a positive one. Now, what do I have here? This is 2 times Q1 shifted with 1 position, which in my case is multiply with 10. Then I have 60, and now I'm trying to find if there is a digit, Q1, in my set, which can fulfill that equation. And I see, if this is 1, it's already 61. Then cannot be more than that, then this is 0. Now, I'm not doing anything, actually I'm subtracting 0. But I'll move a step forward, and my next approximation for the square root is 30. And I arrive to the last iteration, then I have the previous result, I bring into the calculation the last group, and now I do the same. Then the previous value times 2, shifted with 1 position, then multiplied by 10, then is 600. And now I'm looking for a value here, which will fulfill this. And you have to believe, Farhami, that 8 is a good choice. 9 probably will give you a negative result. And 7, it's not large enough. And then I'm done. I have 308, and this is my reminder. And I can check the 308 square plus that is giving me whatever. It looks strange, right? Then there is a complication. first iteration I'm doing something which is different than in next iteration. But in the next iterations, actually I'm not doing something which is very strange. It's, right, it's a shift, what I'm doing. And now I'm looking for some numbers. If I am in binary, things may be easier than if I am in decimal, as in here. In here, in decimal, this is difficult. Now, this is a kind of similar view on square root and division. Basically, what you are looking now is you are looking for the digits of the quotient, which it's also a dividend. Then those, in division I know this and I know this and I'm looking for those. In square root I know only this and I'm looking for those, and they are in the same way. And somehow things are going in a similar way as in division. Now, let us look at the justification for the weird thing that I've done. Then, assuming that I am, you know, I'm attaching a new digit to my square root, okay? Then, attaching the new digit means I will multiply with 10 and I will add the new digit. This is exactly what we are doing in here, right? Then I multiply with 10 and I'm adding a new digit. Now, the square of this guy is this one. However, the 100 qi square, which is 10 qi square, I already subtracted from the number in the previous iteration. Remember the previous iteration, my initial iteration? It was 3, and I subtracted from the number 3 at power 2. Then now when I'm padding the number and I'm keep on extending it, there are things which I already subtracted. Then I cannot subtract twice. And now because of that, what I have is this is what remains, which I can write in this nice way, and then is 2 previous value multiply with the radix plus multiply with this. Now if I go in radix 2, this will result in this one. Then this is my previous approximation of the square root. Now I shift that with 2 positions and I add a 1. Because I shift with 2 positions, I have 2 zeros, right? And adding a 1 will not result in any kind of carry. Then this I can compute with just a shift and padding with a 1. Then essentially, I just have to know whether or not I can do that or I cannot. But I will apply the principle of the restoring division. I am assuming that I'm lucky and I make a subtraction with this number, okay, which is my previous square root padded with 0, 1, because this is equivalent with that addition. And then I'm making a trial subtraction. If the result is positive, guess what's good? I can continue. If not, I have to restore. Then what was looking like a very difficult job is not that difficult after all. You have here an example of how square root is going now in binary. Again, I'm splitting in groups. Then for the first one, it's 1, and now I'm going to the next iteration. Is this value larger than what I obtained from the previous iteration, which is I shift one with 2 positions and I pad with 1? No, it's not. Then I will do restoring. Then I'm not doing anything. You know, the answer to that question is actually a subtraction. I'm not doing it because I'm doing by visual inspection. Now I go to the next one. Then I had 1. Now my square is 10. Again, is this value larger than this? Yes, it is. Then I will report the 1 and I will do my calculation. And now it's the final iteration. And in the final iteration, there is nothing I can do, and this is my result. Then practically, it's an iterative process. It looks like division. The way I form the, let's say, what I'm subtracting is different. Because in division, I was subtracting A, 2A, 3A, depending on the radix. In here, I'm subtracting different things, and I also can do this in a higher radix. Now, this is how things are done in radix 2, and this is consistent with the IEEE format. And we start with the radicand, which is between 1 and 4. It is normalized as a number in that region. This will bring me to a square root, which is always 1 in the most significant position, and then I'll get some kind of fractional numbers. Because this is smaller than 4, I can never get 2. Then it will be between that and that. And this is what I'm applying, you know. I'm choosing, I'm doing a subtraction, and in that subtraction, I actually use this kind of padding. Then this is my number. I always have a 1 in here because of the way things are done. My previous digits padded with 0, 1. I'm subtracting. If result is positive, I'm in business. If result is negative, I am doing restoring. And in here you have the algorithm. Okay. In the first iteration, I have 1 and I'm subtracting 1. That's simple. And from now on, I am trying to subtract the values which are obtained by shifting the partial root and padding with 0, 1. And then you see I'm evolving and I'm evolving to the result. Now, I can also do sometime 1 extra iteration, because the reminder now doesn't really give me any information. In division, the reminder had to have the same sign with the dividend. In here, the reminder is not bringing me any kind of information. However, if I allow for an extra digit in the calculation, then I make an extra precision, that can tell me whether or not I may do a rounding, and I may get now closer to the square root while getting a negative result. But I am closer to the square root, and my goal is to be as close as possible to get the best approximation of the square root. Now, if you look at the hardware is the same. You remember the division? This is the divisor. I was selecting whatever I'm doing, addition, subtraction, that will tell me about the quotient. In here, it's practically the same. Then I can share the hardware between those guys. Just the logic in here is slightly different. And I need a wider header because now I have to pad my number. Then I am shifting with 2 positions And essentially that one at the end, it's actually the carry into the other. Okay. Now this is, I already told you that. You see that if I am doing an extra iteration, I can get closer to the number, but now I have a negative reminder, which I don't care because the reminder is not telling me anything. Okay. Now, remember that for division, we are not happy with the restoring, because restoring creates complications. I'm making a trial, and then I'm deciding whether or not this is good. And there is an extra latency in that. The idea is if you can do also non-restoring square root, then to allow for the result to be negative for a while. And now you can do that, but you have a problem. If you do that, you know, you have to solve the problem later on. And now what you see is that I'm doing for addition and subtraction, this number, it's easy to obtain. It's a shift and it's a padding here. This number is not that nice, because here I really have to subtract it. Then it will not work. That addition is working because I always have whatever and 0, 0 here at the end, and I'm adding a 1, and that's it, there is no problem. But when I come with a -1 here, I have to borrow things. Then this will be like an addition, and I don't like that. Now luckily, this can be solved, and in here, you see the non-restoring algorithm, how it works. Then you have now 1 minus 1 whatever, and you obtain the right result. And this is the trick why this can work. Because what you have is to add or to subtract those combinations. The first one is simple and we know how to solve it. The other one is not very nice. And then what we do is we keep now the quotient, the square root, and the diminished by 1 square root. Then the current value of the square root and the square root minus 1. And then we keep them, and we change the rules of update. Then I have, this is my square root, and when I have a 1, you know, I'm updating it with this one. But this is the diminished by 1 value, the Q star. Now, this Q star can help me to form this amount by only shifting. Because shifting and subtracting 1, it's equivalent with shifting Q star, which is Q minus 1, and adding 3. Then in this way, I solve the problem, which allows me to do non-restoring square root in the same way I was doing non-restoring division. But there is that kind of extra complication that now I need to registers. Then I have some bookkeeping which will require to store the partial root and the diminished by 1 partial root. And now depending on what I have, I will use one or the other, and I will report 1 and minus 1, and I can do on-the-fly conversion. Now the question is whether or not I can do high radix, and quite sure I can, but things are getting more complicated. And you know, this is a radix 4 square root, where again, based on this principle, I have a more complicated stuff to do, then I will keep the register and the diminished by one register, but now the digits are like in division between -2 and 2, and depending on the digit I'm doing things. Idea is the same. I have to get convergency. Then I am always diminishing the number to get to the result. And practically, you can do all the tricks you could do in division, and there is even a possibility to use the same kind of lookup table that you are using in division and do square root. Then in practical designs, okay, we stop here. Then in practical designs, most of the time the divider can also do square root with the proper adjustment of those coefficients. Then I think we are done for today. Next time we'll speak about the last homework, and I'll try to tell you something about Cordic, which is a very nice way to compute whatever you want. It's again a convergency method, but it's a very nice one.